Look at an old photograph. One from your childhood, perhaps. The colors have started to fade. The edges are worn. The memory it holds feels distant, the details blurring. One day, the light will bleach it completely white. The paper will crumble. The image, the moment, the information will be lost. This is our human experience. Things decay. Memories fade. Stories end. Loss feels like a fundamental law of the universe. Now take a book, a history, a novel, your own diary, and set it on fire. Watch the pages curl and blacken, the ink turning to smoke and ash. The story, a complex arrangement of characters and plot, seems utterly annihilated. But physics, in its most profound and arrogant declaration, tells us we are wrong. It makes a promise. A sacred vow. It says that not one single letter of that story has been destroyed. Every last bit of information, the curve of every S, the dot of every I, is still there, scrambled and encoded in the thermal signature of the smoke, in the exact position of every particle of ash, in the ghostly dance of photons radiating away. If you had a machine of impossible power, a cosmic computer, you could capture every wisp of that smoke, every particle of that heat, and you could perfectly reconstruct the book. You could read the lost story again. This is the law of unitarity, the cosmic conservation of story. Information cannot be created or destroyed. It is the bedrock upon which all of science is built. So what happens when we take that promise and throw it into the one place in the universe where all laws seem to break? The one object that seems built for the sole purpose of destruction. A black hole. Here, at the event horizon, the two greatest ideas in human history collide: Einstein's gravity, the law of the macrocosm, and quantum mechanics, the law of the microcosm. And they go to war. At stake is not just the fate of a book, but the fate of reality itself. Does the universe keep its promises? Or does it, in the end, forget? Before we descend into the abyss, we must understand the full weight of this promise. Unitarity is not just a nice idea. It is the constitution of the cosmos. It means the movie of reality can always be rewound. Perfectly. Without a single glitch or missing frame. If you have a complete description of the universe in this exact moment, the position and momentum of every single particle, unitarity guarantees that one, and only one, history led to this state. And one, and only one, future will follow from it. It's the principle of cause and effect written into the source code of existence. The past determines the future, and the future holds a perfect memory of the past. If information could truly be lost, if a single bit of data could permanently vanish from reality's ledger, this entire logical structure would collapse. The movie would have a jump cut with no explanation. Rewinding would hit a dead end. The link between then and now would be severed. Physics would lose its predictive power. It could tell you what happened, but not why, and it certainly couldn't tell you what will happen next. Science would cease to be a predictive engine and would become mere record-keeping. This is why physicists have defended unitarity so ferociously. It is their core belief. It is the contract that the universe signs with itself, promising that reality makes sense. For most of the 20th century, this promise was never seriously challenged. Until Stephen Hawking went looking for a wedding between gravity and the quantum world, and instead, stumbled upon a funeral. In the world of classical Einsteinian gravity, a black hole was the perfect prison, an information fortress. Whatever you threw in, a spaceship, a planet, a library of books, would cross the event horizon, the point of no return, and its story would be sealed away from the rest of the universe forever. The black hole would get a little more massive, a little bigger, maybe spin a little faster. But all the intricate details, all the rich information about what it just ate, was hidden behind an impenetrable wall of warped spacetime. Lost to us, perhaps, but not lost to the universe. It was still in there. Safe. Accounted for. Unitarity was weird but fine. But Hawking knew the universe wasn't just classical. It's quantum. And the quantum world is a restless, chaotic place. He focused his attention on the supposedly empty space right at the edge of the event horizon. And he asked a question that would change everything: what happens to the quantum foam here? See, the vacuum of space isn't empty. It's a simmering stew of virtual particles. All the time, everywhere, pairs of particles and their antimatter counterparts are popping into existence from borrowed energy, living for an infinitesimal moment, and then annihilating each other, paying the energy debt back to the vacuum. It's a constant cycle of creation and destruction on the smallest of scales. A quantum fizz. Hawking did the terrifyingly complex math. He calculated what happens when a pair of these virtual particles is born right on the precipice of a black hole's horizon. He saw that it was possible for one member of the pair to be captured, falling into the black hole, while its partner escapes, flying off into space. Now, for the universe to keep its books balanced, something clever has to happen. The particle that falls must carry negative energy. It's an energy debt. When the black hole absorbs it, it pays that debt by losing a tiny, tiny fraction of its own mass. The particle that escapes, meanwhile, flies away as real, positive energy. To a distant observer, this stream of escaping particles looks like a faint, thermal glow. It looks like the black hole is radiating heat, like a piece of hot coal. We call it Hawking radiation. And the implication was staggering. Black holes are not eternal prisons. They leak. They evaporate. And over truly astronomical timescales, longer than the current age of the universe, they will radiate away their entire mass and vanish in a final puff of energy. And in that final puff lies the paradox. Hawking's calculations showed that the radiation coming out was purely thermal. It's random. It's generic. Its only characteristic is its temperature. It's like the hiss of static from a radio tuned between stations. It carries no information, no story, no structure. So if you throw a beautifully complex encyclopedia into the black hole, and the black hole slowly turns that encyclopedia into featureless, random static, and then the black hole itself completely disappears. Where did the information go? Hawking's own conclusion was a dagger to the heart of physics. It's gone. Erased. Deleted from the universe's hard drive. Unitarity, the unbreakable promise, was broken. The cosmic contract was void. The movie of the universe couldn't be rewound. Physics, for the first time, was facing the possibility of true, irreversible loss. The community was in turmoil. A 40-year war had just begun. So how do you defend reality from its own laws? You conduct an audit. The most important audit in the history of science. The battlefield for this war was a graph. A simple-looking curve that would represent one of two destinies for our universe. This is the Page curve, named for physicist Don Page. To understand it, we need to think like cosmic accountants, and our job is to track a quantity called entanglement entropy. That sounds intimidating, but all it really is an ignorance meter. It's a measure of how much information is hidden from you. Imagine our black hole is a box, and it's emitting Hawking radiation, one particle at a time. Each particle that escapes is deeply, profoundly entangled with its partner that fell into the box. They are two sides of the same coin. A quantum secret shared between the inside and the outside. As the first particles of radiation fly out, you collect them. But they tell you nothing about the encyclopedia that's inside. They are only entangled with their partners still trapped in the hole. So your ignorance about the encyclopedia grows. The more radiation you collect, the more entanglement there is between the outside world and the inaccessible inside of the black hole. Your ignorance meter, the entanglement entropy, climbs. And climbs. And climbs. This is path A. This is what Hawking's original calculation showed. A straight, relentless line, rising as the black hole evaporates. If this path is correct, your ignorance keeps growing until the very end. The black hole disappears, and you are left with a cloud of hot, random radiation that is still maximally entangled with nothing. An empty space where the black hole used to be. This is a mathematical absurdity. It is the signature of information loss. This is the graph of a universe with amnesia. But if unitarity is true, if the unbreakable promise holds, the graph must look different. This is path B. Don Page and others argue that for information to be preserved, it must eventually come out, encoded in the radiation. So, for the first half of the black hole's life, your ignorance meter rises, just as Hawking said. But then, something magical has to happen. At a point now called the Page time, roughly when the black hole has radiated away half of its mass, the trend must reverse. The new radiation coming out can no longer be entangled with the dwindling interior. Instead, it must be entangled with the old radiation that has already come out. The puzzle pieces must start fitting together. The story of the encyclopedia must begin to emerge from the static. This means that after the Page time, your ignorance meter must peak, and then it must start to fall. With every new particle of radiation you collect, you learn more about the whole story. Until, at the very end, When the last particle emerges, the black hole is gone, your ignorance meter hits zero, and you now, in principle, possess all the information to reconstruct the encyclopedia. This iconic shape, a curve that rises, peaks, and then falls back to zero, this is the page curve. It is the graphical proof of unitarity. It is the signature of a universe that remembers. For decades, this was the goal. The Holy Grail. Make the math of gravity and quantum mechanics produce this beautiful curve. But no one could do it. Every calculation just produced Hawking's rising line of amnesia. It seemed the universe was built on a paradox. A brilliant, temporary peace treaty was proposed to try and solve it. This truce emerged from another bizarre property of black holes that we touched on earlier, the holographic principle. The discovery that a black hole's information content scales with its two-dimensional surface area, not its three-dimensional volume, was a profound shock. The wallpaper in the Library of Congress doesn't just describe the books, it is the books. This wild idea suggested that maybe our 3D reality is just a holographic projection of information living on a distant 2D boundary. Physicists Leonard Susskind and Gerard T. Hooft used this holographic flavor to propose black hole complementarity. The idea was as elegant as it was radical. The truth about what happens to your encyclopedia depends entirely on who you are. Reality is observer-dependent. Let's say you are a brave astronaut, Alice, and you decide to jump into the black hole, carrying the encyclopedia with you. From your perspective, you would sail right across the event horizon without any drama. No walls, no fire, just a smooth transition. Einstein's theory holds. You and your book are inside, on your way to the singularity. For you, reality is normal for a short while. Now let's consider your friend Bob, watching you from his spaceship at a safe distance. From his perspective, things look very different. Due to the extreme gravitational time dilation near the horizon, he would see your approach slow down. As you get closer, you appear to move slower and slower, until you seem to freeze just above the surface, getting redder and dimmer, smeared across the event horizon over an infinite amount of time. From Bob's perspective, you and your encyclopedia never actually cross into the black hole. Your information is splattered, scrambled, and thermally radiated back out into space as Hawking radiation. So who is right? Alice, who fell inside with the book? Or Bob, who saw the book get vaporized and radiated away at the edge? Complementarity's genius answer was, both. Since Alice, once she crosses, can never send a message back out to Bob, and Bob can never look inside to check on Alice, their two contradictory descriptions of reality can never be directly compared. So there is no paradox. As long as no single observer can see both outcomes, the contradiction doesn't exist. It was a clever truce between quantum mechanics, information is radiated out for Bob, and general relativity, the horizon is smooth and uneventful for Alice. And for nearly 20 years, it was the best answer we had. The war was cold. A fragile peace held. Until, in 2012, four physicists known as AMPS decided to poke the sleeping dragon. The paper by Almhiri, Merolf, Polchinski, and Sully, AMPS, was an act of intellectual terrorism against the fragile peace of complementarity. They demonstrated that you don't need to compare Alice's and Bob's points of view. A contradiction existed in Bob's experience alone. They conducted a thought experiment. Imagine Bob has been patiently sitting outside the black hole for a very, very long time. It has already passed its page time, it's old and has radiated away more than half its mass. Bob has collected all this early radiation, let's call it System A for Alice. Now, a new particle of Hawking radiation emerges from the black hole. Let's call this new particle B for Bob. And let's not forget the particle that fell into the hole, the antimatter partner of B. We'll call it C, for Charlie, trapped behind the horizon. Here is where the crisis erupts. Our hero, particle B, is trapped in a quantum love triangle, and the universe has a strict, non-negotiable rule about relationships, the monogamy of entanglement. This law is fundamental. A quantum particle can be maximally entangled with one, and only one, other partner. Think of it as a perfect marriage. You can't be perfectly married to two people at the same time. The quantum bonds are exclusive. Particle B, Bob, has two contradictory obligations. Obligation 1, to save unitarity. For the page curve to fall, and for information to be preserved, the new radiation, B, must be entangled with the old radiation, A. B must be entangled with A. This is the only way the encyclopedia's story gets out. Obligation 2, to save spacetime. According to our understanding of quantum fields, for the event horizon to be a smooth, normal-looking patch of space, the no-drama scenario, particle B must be maximally entangled with its interior partner, C. This entanglement across the horizon is what stitches spacetime together. So, B must be entangled with C. Do you see the problem? Bob, particle B, must be perfectly married to Alice to save information, and it must be perfectly married to Charlie to save spacetime. It can't do both. Quantum monogamy forbids it. So something has to give. You have to pick your poison. You have to break one of the marriages. Choice 1. You break the bond between B and A. This means B is not entangled with the early radiation. The information doesn't get out. The page curve goes up forever. Unitarity is violated. The universe has amnesia. Physics breaks. Choice 2. You break the bond between B and C. This is the bond that stitches the horizon together. What happens when you violently sever a quantum entanglement bond? It releases an enormous amount of energy. The MPS argue this is what must happen. The bond between B and C must be broken. And the result is a cataclysm. The smooth, drama-free event horizon is replaced by a seething, incandescent shell of high-energy quanta. A literal wall of fire. An astronaut like Alice, thinking she was falling into a quiet abyss, would instead slam into a boundary where spacetime itself dissolves, and she would be instantly incinerated into her constituent particles. The no-drama horizon was a lie. The Firewall paradox was a complete disaster. It told us we had to choose between our two most successful theories. Either unitarity was wrong, or general relativity was wrong at the horizon. The beautiful truce of complementarity was dead. The war was hot again. Physics was shattered. And for nearly a decade, no one knew how to pick up the pieces. The universe had presented us with an impossible choice. But what if the choice itself was based on a flawed premise? What if our accounting was simply wrong? For years, the brightest minds in physics slammed their heads against the firewall. And then, slowly, a revolution began. It didn't come from a new particle or a dramatic experiment. It came from a new, more powerful way to do the math. A new way to conduct the cosmic audit. The crucial breakthroughs involved names like Netta Engelhardt, Aaron Wall, Jeff Pennington, and Ahmed Almhiri, one of the original Firewall instigators. And their work centered on a new, more complete way of calculating entropy, leading to the discovery of quantum extremal surfaces and a shocking new character in our story, the island. Let's return to our cosmic accountant. Their job is to calculate the entropy of the Hawking radiation, our ignorance meter. The old way was simple. You draw a circle around the radiation, far from the black hole, and you calculate the entropy inside that circle. This method always gave you Hawking's line of amnesia. But the new rule, the quantum extremal surface rule, was a game changer. It said, when you calculate the entropy of the radiation, you must find the boundary that makes the total entropy as small as possible. And this boundary doesn't have to be simple. It can have multiple, disconnected pieces. Imagine the accountant is looking at the radiation, system A. They calculate its entropy. It's a high number. Then, the new rulebook tells them to try something crazy. Now it says, add a second circle to your calculation. A circle located deep inside the black hole's interior. A disconnected region. An island. At first, this doesn't help. Early in the black hole's life, adding this island just makes the total entropy bigger. So the accountant ignores it. The extremal surface is just a circle around the radiation. And the ignorance meter goes up. But then comes the page time. The black hole is halfway evaporated. The accountant does the calculation again. And something miraculous happens. They find that if they include a specific island region inside the black hole as part of the system of the radiation outside, the total combined entropy is now lower than the entropy of the radiation by itself. According to the new rules, this is the correct answer. The extremal surface now has two pieces, one around the distant radiation, and one around the island deep inside the hole. The accountant has just been told that for the books to balance, a piece of the black hole's interior now officially belongs to the radiation's ledger. It's a quantum rezoning of spacetime. When you use this new accounting method, with the island included after the page time, and plot the entropy, it perfectly traces the page curve. It rises, peaks, and then falls. Information is not lost. Unitarity is saved. The firewall is averted because the entanglement that seemed to cause it, between B and C, is now understood as entanglement within the greater radiation system. B and C are on the same team, just in different locations. No monogamy is violated. The paradox dissolves. But this raises an even deeper question. How can a piece of the interior be part of the radiation that's trillions of miles away? What connects them? The answer is the final, mind-bending piece of the puzzle, and it might be the most profound insight of 21st century physics. The connection is a wormhole. Or, more precisely, a vast web of them. These are called replica wormholes, and they appear in the mathematics used to calculate the entropy. They are not traversable tunnels you could fly a spaceship through. They are deeper, stranger connections in the geometry of spacetime itself. They are the mathematical manifestation of the entanglement between the island and the radiation. This gives concrete mathematical power to a radical idea that had been floating around for years: ER equals EPR. EPR stands for the Einstein-Podolsky-Rosen paradox, which first highlighted the weirdness of quantum entanglement, that spooky action at a distance. ER stands for an Einstein-Rosen bridge, the technical term for a wormhole. The conjecture, ER equals EPR, proposes that these two things are the same phenomenon. Every entanglement between two particles is, in some deeper, geometric language, a microscopic wormhole connecting them through spacetime. Stop and think about what this means. Spacetime is not the fundamental stage on which the drama of physics plays out. Spacetime itself is emergent. It is built from the network of quantum entanglements. The geometry of our universe is not the canvas, it is the paint. And the paint is entanglement. The universe is not a collection of things in space, it is a network of relationships that creates space. The information paradox wasn't a mistake. It was a signpost, pointing us to this deeper reality. It was forcing us to see that to save information, we had to dissolve spacetime. So we returned to where we began. The fading photograph. The burned book. Our experience of loss. The black hole information paradox, after a half-century of intellectual warfare, has taught us that on a fundamental level, loss is an illusion. Reality is a perfect ledger. A lossless hard drive. The universe remembers everything. What we perceive as an ending, as destruction, is merely a transformation of information into a state of such staggering complexity that it becomes inaccessible to us. The universe keeps its promise to preserve the story of the book, but it locks the diary and melts the key. For all practical purposes, the secret is kept. The cosmic censor isn't some arbitrary rule, it's computational complexity itself. And perhaps this is the most personal lesson. Your life. Every choice you make, every word you speak, every photon of light that carries your image, that information is not fleeting. It is being perpetually woven into the correlations of the cosmos. Your story is not erased upon your death, it becomes a permanent part of the universe's grand, scrambled, and impossibly complex tapestry. The past is never truly gone. It is simply elsewhere in the ledger. Written in a language of entanglement we may never learn to read, but written nonetheless. And it will be there, forever. We have traveled from a burning book to the edge of a black hole, through a wall of fire, and into the quantum heart of spacetime itself. We've learned that the universe has a perfect memory, even if its filing system is a bit chaotic. There is another video on your screen right now. It tackles another of science's epic paradoxes. The algorithm believes, with 99% certainty, that it's the perfect next step on your journey. Go on and click it. But before you go, I have to ask you the question that this entire journey leads to. The realization that an indestructible, perfect record of your entire existence is kept by the cosmos, does that feel more reassuring, or more terrifying? Tell me your one-word answer in the comments below. It's a profound one to think about. And finally, if going on these deep dives into the very nature of reality is why you're here, then you're in the right place. We do this every single day. Hitting that subscribe button ensures you never miss a new page from the Cosmic Ledger. Thank you for auditing the universe with us.